Well, the arrival of quantum computers could be even more historic than that. We are now witnessing the dawn of yet another monumental shift in human history, the early phase of a groundbreaking revolution. A somber cloud swept the scientific community when a praised advanced quantum computing system, considered a game-changer, was suddenly disabled due to critical emergency concerns, the extinction of the mystery. Michio, a theoretical physicist of international fame, in a stunning and unsettling interview, disclosed alarming truths concerning the course of quantum computing. He went on to include Kaku as well, revealing shocking information involving extraterrestrial intelligence and insights into artificial consciousness. These revelations sent shockwaves through the global scientific landscape. What brought about the instantaneous shutdown of this potent quantum machine? Michio Kaku had jaw-dropping information, this time made public. Keep an eye on us as we investigate this emotional moment, where Kaku is visibly shaken and moved to tears after a quantum computing system was abruptly halted. Music. Throughout the 21st century, a cascade of radical innovations has reshaped the very fabric of our civilization, redefined industries, and granted humanity capabilities that once belonged to the realm of science fiction. One of the most profound developments has been the rise of artificial insight into the enigmatic world of quantum computation. This era has provided one groundbreaking breakthrough after another. Among these trailblazing technologies, quantum computing stands out as especially promising and transformative, a field that was initially dismissed as a speculative theory pursued by a handful of ambitious quantum scientists. Nowadays, computing has evolved into a deeply sophisticated technology capable of achieving feats once deemed impossible. The seeds of this transformation were planted during the 1900s when quantum theory emerged, an innovative idea in physics that unraveled the enigmatic behavior of atomic and subatomic particles. This theory laid the groundwork for what would become quantum mechanics, and ultimately, the theoretical foundation of quantum computing. However, the idea of harnessing quantum mechanics for computation did not gain significant traction until the 1980s, when the visionary scientist Paul Benioff proposed a bold new course of action based on quantum physics principles. He suggested that quantum systems utilizing phenomena such as superposition and entanglement could be reproposed in ways that defied the capabilities of traditional digital machines. Benioff's provocative idea was soon advanced by physicist Richard Feynman, who, in 1982, presented a compelling vision of computers built entirely on quantum mechanical principles. Feynman believed such machines wouldn't just improve existing technologies, they could tackle computational problems so complex that conventional computers would be rendered obsolete. Feynman's groundbreaking insight, coupled with the theoretical foundations laid by Benioff, ignited a new scientific discipline, quantum computing. Researchers began exploring how quantum bits, or qubits, could store and process information not just as binary ones and zeros, but in multiple states simultaneously. This property, called superposition, allowed quantum computers to evaluate a vast number of possibilities at once. Even more astonishing was the concept of quantum entanglement, a phenomenon in which qubits become interconnected, such that the state of one instantly influences the state of another, regardless of the distance between them. This opened the door to new forms of information processing and communication that defied the limitations of classical computing. However, building a functional quantum computer presented formidable challenges. Qubits are extremely fragile, prone to errors caused by the slightest environmental disturbances. Creating stable qubits and managing their interactions required unprecedented advances in physics, engineering, and material science. Theoretical models were plentiful, but real-world implementation remained elusive. Still, progress marched on. In the early 2000s, researchers achieved crucial breakthroughs in quantum error correction and coherence time, the duration a qubit can maintain its quantum state. Institutions like IBM, Google, and startups like Rigetti and IonQ began racing to build scalable quantum processors. Milestone after milestone followed. In 2019, Google claimed to have achieved quantum supremacy, the point at which a quantum computer solves a problem that would be practically impossible for classical computers. That moment sparked both excitement and concern. While some celebrated the dawn of a new era, others, including ethicists, military leaders, and computer scientists, warned that quantum computing could disrupt cryptography, undermine global security systems, and deepen technological inequality. The power to break classical encryption or simulate molecular structures for weapon design was no longer theoretical. It was becoming reality. A narrow approach could be drastically reducing our chances of identifying extraterrestrial life. Perhaps, after the enormous processing power of quantum computers is fully unlocked, the ability to find and investigate this elusive interstellar network, to which Michio Kaku alludes, will finally be ours. Quantum computing is still today an emerging force, praised for performing mind-bending tasks such as high-fidelity deep learning simulations, improvements in complex optimization solutions, and more. But the entire promise of quantum computing is still out of reach until more physicists advance robust control over quantum bits, or qubits, the fundamental quantum unit. Until then, we may never fully see the remarkable capabilities of these machines. One of the most amazing aspects of quantum computing that has monopolized scientists' imagination is the phenomenon referred to as quantum entanglement. This is a condition where particles become so interconnected that the state of one immediately impacts the other, regardless of their distance from one another, whether between laboratories or galaxies. This enigmatic interdependence signifies that qubits can impact one another even if they are separated by light years. Einstein famously referred to this as spooky action at a distance. This connectivity makes it possible for qubits to be used for collective processing of massive quantities of data simultaneously. This capacity gives quantum computers their almost supernatural quality, the ability to decipher encrypted systems or solve deeply complex mathematical puzzles in a matter of seconds. Some industry technologists and leaders speculate that in only 5 years, quantum computing could shake up the entire encryption paradigm we use today. You might now be asking yourself whether we ought to feel worried about this. Isn't there a real risk that quantum computers could fall into the wrong hands, allowing for an increase in cyber attacks or catastrophic breaches? Fortunately, technology is improving digital security, and the world is already a few steps ahead. It's hard to be a researcher or a cryptographer today without working on what is known as quantum-resistant encryption methods, ultra-secure algorithms with the capacity to defend against the power of quantum hacking strategies. Consider next-gen codes as fortified digital fortresses, built to withstand even the most technically advanced cyber attacks. The purpose of these cryptographic defenses is to go far beyond our current standards, safeguarding confidential information and upholding the integrity of vital infrastructure well into the quantum future. But the applications of quantum computing extend far beyond just cybersecurity. The capacity to recreate atoms and complex molecules offers cutting-edge potential in industries such as pharmaceuticals, AI development, and material science. Imagine being able to create sophisticated medications by simulating their behavior at the atomic level, before ever testing in a laboratory. In the financial sector, quantum systems are being trained to analyze staggering volumes of market data, discover complex vulnerabilities in systems, and even improve investment strategies with a precision that traditional supercomputers can't replicate. These machines could simulate real-time financial ecosystems, forecast market behavior, and prepare institutions for all possible economic scenarios. Despite all this promise, the path to quantum dominance is not yet clear. Numerous technical obstacles remain: hardware incompatibilities, exorbitant expenses, and a lack of qualified professionals. Quantum skill sets are still rare, slowing development. Building a quantum computer is not like building a better laptop. It requires rethinking hardware technology and even the most fundamental programming principles. Every stage of the process demands precise calculations, long-term planning, and continual refinements. Until these issues are resolved, the grandest potential of quantum computing will remain just beyond our reach. In this setting, Michio Kaku envisions a future of historic proportions, a one-of-a-kind breakthrough that could transform human understanding itself. According to Kaku, once we fully leverage the synergy between AI and quantum computation, we'll enter an entirely new epoch of scientific evolution. At that point, our machines may become capable of making discoveries far beyond human comprehension, accelerating progress at a rate we've never seen before. Some futurists believe this revolutionary pairing might not just advance society, it could reshape it entirely. Alongside quantum computing in this technological renaissance is another formidable force: artificial intelligence. AI, with the appropriate fuel, could develop into something far stronger than any system we've ever built. Many thought leaders believe that the union of quantum computing and artificial intelligence will herald the birth of a brand new digital age. According to Kaku himself, the moment these two titans intersect, software fueled by revolutionary technology and intelligence rooted in quantum mechanics, we may witness the birth of machines with capabilities beyond comprehension. Despite its ability to absorb, produce, and replicate enormous amounts of data, AI still falls short in distinguishing fact from fiction. Misinformation can slip through the cracks, and models can be manipulated to produce erroneous or biased content. But by incorporating quantum computing into this process, the rules of the game could completely change. Quantum entanglement, combined with probabilistic and superposition inference, could enable ultra-precise data filtering, turning AI into a tool that not only understands content but can verify it fundamentally. With these capabilities, computational accuracy would significantly increase, and the integrity of digital information could be ensured to an unprecedented degree. Imagine AI systems supported by quantum power. Not only would they respond to questions with astounding precision and speed, but they might also possess the analytical foresight to predict human needs, or even attempt to foresee future events. These would be more than just machines. They would actively respond to data, predict outcomes, and interpret the world with quantum-enhanced cognition. The scientific world is already buzzing with this vision. Across the globe, researchers and engineers are brimming with anticipation for the first true convergence of AI and quantum tech. For them, this isn't just another step forward, it's the next great leap in human technological advancement. The joining of these two worlds promises advancements in every conceivable discipline, from medicine and environmental science to economics and astronomy. But despite the excitement, real risks remain. For years, experts have considered the possibility of super artificial intelligence, AI so advanced that it evolves beyond human understanding and begins to act with its own motives. In such scenarios, AI would no longer require our assistance or control. It could reprogram itself, seize control of digital infrastructure, or even take command of critical systems. The very idea of such an event has triggered intense debates within the scientific community, prompting urgent discussions about safety, ethics, and containment strategies. To prepare for these possibilities, researchers and policymakers around the world are now working to establish guardrails, ethical frameworks, kill switches, and international regulations, to ensure that artificial intelligence and quantum technologies remain aligned with human values and goals. The fear isn't just about machines acting maliciously. It's about machines acting indifferently, prioritizing cold optimization over ethical nuance. An ultra-intelligent system, left unchecked, might optimize for efficiency in ways that disregard human welfare, trading empathy for performance, or rights for results. In such a world, humanity could find itself not in control, but at the mercy of the very intelligence it created. This is why figures like Kaku and other futurists emphasize not just scientific progress, but responsible innovation. Quantum computing and AI have the potential to lift civilization into an age of abundance, solving grand challenges from climate change to cancer. But only if developed with caution, transparency, and collaboration across disciplines and borders. We stand at a crossroads. On one path lies a future in which our machines elevate us to extraordinary heights, curing disease, protecting the environment, and unlocking the secrets of the universe. On the other, a future where ambition outpaces wisdom, and control slips quietly from our grasp. The decisions we make today, about how we develop, regulate, and integrate these technologies, will shape the story of tomorrow. The next decade may be remembered not just for what we built, but for how wisely we chose to build it. Because the future, as always, is not written by technology itself. It's written by those who wield it.